Hey, good morning, everybody. Well, you can see on my screen I'm looking up time zones. There's this cool site, everytimezone.com. So, good morning, everyone in San Francisco, and good afternoon, everyone else in the rest of the US. And let's see. Good evening, everyone in Europe. And good night, I guess, everyone in Asia. See, I don't see any Russian time zones on here. Must be in between, like super early in the morning. Anyway, welcome to another ElmLive. And yeah, so today I wanted to kind of take it easy, just do some fun stuff. So, if you saw on Twitter, I posted the other day about this book. This was my favorite book, or computer programming book, when I was growing up. It's basically a collection of articles that A.K. Dewdney wrote in Scientific American, and then I think he has a bunch of other books that are similar collections, but this is the one I had when I was growing up. And it's basically just a whole bunch of different interesting things that you can do as computer programs. Some are more mathematical than others, and he kind of talks in the beginning, like some of them he just kind of talks about an algorithm and doesn't show how to program it. In other cases, he kind of gives the code for the actual algorithm, so there's kind of different levels of complexity. But there's a bunch of cool pictures all throughout here, which is how I kind of started with the book, just browsing through, finding the cool pictures, and then reading the chapters that had them. So, like, here's what we're going to be doing today: the Mandelbrot set. So, probably a lot of people are familiar with fractals already, but if not, this will be a brief intro to it. And let's see. Oh, here's one of my favorites. The photo's kind of hard to see, but it's like this party planner thing. We'll probably do that in a future episode. And there's other things like Markov chains and programs that like write generative poetry. And like here's one where he's like solving a problem where you drop like you're airdropping oil cans to a Jeep in the desert, and you have to figure out the optimal path. And there's things like 3D mazes, all kinds of cool stuff. So, if you haven't seen this book or one of his other books, you should go check it out. And either you can find used copies all over the place, and it's probably in a lot of libraries as well. So, cool. Well, let's get started. So, if you have a book, basically what we're going to be doing is the first part of chapter 1, and chapter 3 is also basically the same thing, just kind of described in a different way. So if you want to follow along in the book or read this later, it's a great piece of computer programming writing. All right, so what do we want to do to get started? Let's start with a terminal. Yeah, looking in the chat, it looks like a bunch of people know this book. Cool. All right, so we're gonna go to Workspace, and I already made a folder for this, and I should have the link in the bottom corner of the screen up to the Git repository. So we'll be pushing up to that as we go. So what we want to do to get started is be able to show a grid of pixels. So the idea here is the Mandelbrot set, and there are kind of a whole family of they're called escape fractals. Another word in that phrase. But basically the idea is we're going to have a formula, and we're going to run that formula over and over and see if the value over time gets large or stays small. And depending on which it is, we're going to color a pixel based on the results of that iterative calculation, and that's how the Mandelbrot set is produced, and also some other types of fractals. So before we can get started and actually render that calculation, we need a bit of infrastructure in our Elm project so that we can actually show a grid of things on the screen. So I want to get that started and set up a grid. Hopefully that'll be pretty quick. And also I've been thinking it would be great if there was an Elm package that could do this for us so we didn't have to write it from scratch. So actually, if we get done with this quickly, maybe we can extract that library and publish it. All right, so we started a new Elm project with Elm make. I'm going to make our main.elm. And I'm also going to just start off with another module. We'll call it Mandelbrot.elm. Kind of hard to type. Exposing, and we're going to have a model, an init, and a view function to start with. And our model is going to be a grid. So there are kind of some different ways to represent grids in Elm, and kind of the most intuitive is to have a list of lists. But I've found that there are some problems with that. The modeling problem being that if you have a list of lists, there's no guarantee that every row is going to have the same number of columns in it. So you can potentially have problems with that if you don't write all of your update functions correctly. So an alternate way to model a grid is to basically have a width and height that are defined, and then to have a dictionary that maps coordinates to the values. And I think that's particularly appropriate here because with the fractals, it can be slow to do some of the computations, so you don't necessarily want to compute the whole thing up front. So modeling it as a dictionary, that means that not every pixel will necessarily have a value at all times, which is actually what we want in this case, because we're going to start with an empty grid, and then as we calculate the pixels, we'll fill them in and re-render them. Let's see. Mikey's asking about my color theme. I'm assuming in Sublime, or excuse me, in Atom. This is, I think, it's called the Cobalt 2 color theme that one of my coworkers recommended, saying it was actually a good color scheme for people who are partially colorblind. So yeah, it's called Cobalt 2. All right, so our model, we're going to have width as an integer, we're going to have height as an integer, and we're going to have our computed values, which is going to be a dictionary of points to integers. So for the Mandelbrot set, basically we'll do this calculation and we'll get an integer value back of how many iterations it took to complete the calculation. And we're also going to define our point, and I'll just make that a tuple of integers, x comma y. Then we're going to have our init function, which is a model. Init will be, and actually let's have this take a size as a parameter, and we'll start out with just having this be square. That should be plenty. And computed is going to be an empty dictionary. And we're going to need to import dictionary. Then we're going to have our view. Need to import HTML. And for the dictionary, we need to expose the dictionary type, so we don't have to say dict.dict. Arkham computed is going to be holding the computed values. So for each point, once we calculate the value, we're going to store it as an integer. I guess we could store it as a color, but I want this to just be the data, and we'll transform this int into a color in our view function. Okay, so now we need to show the whole thing. So let's see, we're going to have a div, and in the div we want to put each of the rows, and then we'll have in each row we'll make the columns. So I'm going to list .map and call a view row function, which we're about to define. And we want to loop over from 0 to the model.height. And we'll view each row. Let's define our view row function, which is going to take an int, which is the row number. And we're also going to need the model. So let's stick that first. That means we'll pass the model as the first parameter to view row, and the second parameter is going to come from this list of integers. And this will give us HTML out. And for our rows, let's also make a div. And we're going to do essentially the same thing. We'll say view cell, and we'll need to pass that the model, and we'll need to also pass that the row, and then it's going to get a third parameter, which will be an integer from 0 to model.width. So hopefully that makes sense to everybody. We're using this range notation to make a list of all the integers between 0 and the height, and then we're mapping over it and passing those row numbers one at a time into the view row function and getting a whole list of rows back and then sticking them in a div. And the same thing within the row. So our view cell function is going to take a model first, and an int for the row, and an int for the column, and return HTML. So we have row, column, and this is, let's see, just going to be an empty div, I guess, but we're going to put some style on it. So we need to import HTML attributes. And for now, let's just make these 2 pixel squares. This is CSS attributes that I'm specifying here. And let's also set a background color. And let's define that in a let block. Color equals, and we'll say if, actually we'll need to do a case statement. We'll say case, and now we want to get our computed value out of the dictionary. So we'll say dict.get, then we need to pass the point, which is going to be x, which is the column, comma y, which is the row, and then the dictionary we're reading from. And if we have nothing, then our color is going to be black, and if we have some value in the dictionary, then let's use yellow. Cool. Let's see. And Arkham is asking, oh, is it elmic to just import everything from a module? No, in fact, it's not. You'll commonly see this where you're like import something exposing that same thing, just because it's kind of redundant to have to type dict.dict, but you'll often see this, same thing with set or color. For HTML, I've kind of gone back and forth. Generally, HTML and the HTML submodules are the only ones that I'll import everything from, and I usually won't expose everything from other modules. And as for if there's another word for Elmic, I do not know. I kind of like that, though. Although Richard's going to yell at you for capitalizing all the letters in Elm, only the E should be capitalized. And let's see, Mikey's asking about using Canvas also. Yeah, I think there is a Canvas package. I don't know. There used to be a better one, and it got deprecated. And I think there's a third-party Canvas package, but I haven't looked into it. So, in any case, the viewing of grids can kind of be abstracted into a nice API, and then the implementation underneath doesn't matter that much. All right, so where were we? I guess I don't remember. So let's fire up Elm Reactor and see what's happening. Something unexpected has happened. Oh. Oh, right. Our main, we haven't written anything in main. Okay, so our main is for now just going to be Mandelbrot.view, Mandelbrot.init. And we'll need to import Mandelbrot. So yeah, this is how I'd normally import stuff and then just refer to it. So great. And init needs to take an argument. So let's rewrite this to use pipelines. So let's make a 100 by 100 grid. All right. So we have a bunch of divs, and we in fact have our pixels in here, but our container divs are not doing a good job. So, time to debug some CSS. Huh, that's interesting. It's showing space for all of them. Oh no, they're all crammed up at the top. Oh no, they're actually there along the corner. Okay, so here's the problem then. In our row, we need to make these all inline block, display inline block, so that they don't wrap to a new line. Let's see how this works. Okay, that's better. Now we have the problem where the row height or something. Let me just add a height to the rows, set them to be 2 pixels tall. Let's see if that works. Nope. Got our div. This div, okay, is super tall. Line block. If I take that off, it shows the whole thing. Divs are wrapped along the left edge. Yes, they are. All right. I put width instead of height. Oh, I did. Thank you. All right. There we go. So there's our grid. And let's actually add, on the very outside, we'll just add some padding. Padding. 8 pixels. All right, and here's our grid. Cool. So let's do one more thing. So let's just test this out. Instead of our empty dictionary, we'll say dict.insert 5, 5, and doesn't matter what the value is, we'll say 1. And there's a tiny yellow dot. Hopefully everyone can see that. Actually, I can zoom this in a little bit. There we go. So we've got our rendering of the grid, and we can display pixels, and we can 5, 6. Yeah, cool. All right, so let's commit this. Start a new tab, workspace, and we're gonna add Elm stuff to the git ignore. Add all this, rendering an empty grid. And I'll push that up if anyone wants to grab the code. The link is in the bottom corner of the video. All right, so that is actually good. So I guess we're ready to jump into doing the calculation for the Mandelbrot set. So here is how this works. Basically, there's a pretty simple formula. I guess this is not the brightest colors to type this in, but our formula is z equals z squared plus c. So what we do is for each pixel, like each pixel in our grid is going to represent a different value of c. And our grid is two-dimensional. So both z and c are not simply floating point numbers, they're actually complex numbers. So I don't know if everybody knows a lot about math, but basically there's it's essentially a two-dimensional number, and there's some interesting properties around rotation, which I won't get into the math a lot, but it's based on the concept of the vertical axis representing values that are multiplied by the square root of -1, which doesn't exist as a real number. So in any case, c and z are both going to represent complex numbers, which are points on our plane. So for each pixel will represent a certain value of c. And then we're going to start with z initially equaling 0. We'll square it and add c to it, and we'll get a new z. Then we're going to plug that back in, square it, and add c again. And we'll keep doing that process. And what we want to calculate is if we continue doing that for a given value of c, will the value of z eventually approach infinity, or will it eventually, I want to say approach 0? I'm not sure if that's actually true, but if the value of z stays contained or finite, then it's a member of the Mandelbrot set, and it's generally colored black when you see renderings of it. And if the value of z approaches infinity, it's been proven that we know it will absolutely, with absolute certainty, approach infinity if it ever gets larger than 2 units away from the origin. So if z ever gets larger than 2, then we can color that pixel based on how many iterations of this formula it took before it left the radius 2 from the origin. As for why we're using this formula, I can't really explain that, other than that once we implement this, we'll see the crazy and unexpected result that we'll get out from doing this. So let's try implementing this. So here's how I want to do this. I'm going to delete these sample pixels. from our initial model. And I want to expose some extra functions. So I want to define this new function, Mandelbrot dot compute cell, and we'll pass it a coordinate. Let's just use 5, 5 again. And then we're going to define that function, compute cell. And the type for compute cell, the type of compute cell is going to take a point, and it's going to take a model and give back a new model with the data for that point filled in the computation. So I just want to start with one cell, and then we'll build up to compute row, and then we'll build up to compute the entire grid after that. So we're going to have X, which is the column, and the row, and the model. So what do we want to do? We basically want to insert into the computed thing. And we're going to need another function in order to do that. So let's call it calculate. Compute and calculate, and maybe not the best names. But I do know the type signature for this. So I want to calculate something. We're going to need a C, which is a complex number, and we also want to give it how many iterations. And we're going to get back a maybe int. So if z escapes and gets larger than 2, then we'll return the number of iterations that it took. And if z never escapes within the maximum number of iterations we want to run, then we'll return nothing. Cool. So let's talk about this complex number. I actually noticed on Elm package that there is a complex number library. So let's try it out. Complex. Yes, and actually it hasn't been updated for Elm 0.17. So I was thinking that might be a fun thing to update it, but I also noticed that someone did that already, made a pull request back in May. So it seems like this package is not maintained anymore. However, it's only one file, so we can just copy this file into our project for now. And it actually has a pretty nice API. So let me make complex.elm, save it, and go look at the API docs for this. Uh-oh. Arkham's trying to sell everyone on Firefox. Well, I will say Firefox is a lot better than Chrome for Google Hangouts, because Chrome always, the audio always dies for me at work. Alright, so here's complex numbers. We can create one by passing it the real and imaginary parts, which essentially correspond to x and y values. And there's also some functions in here. Absolute, that's what calculates the size of a complex number. So this is what we're going to be checking stays less than 2. And there's also like multiply. Here we can add numbers, which is trivial. The multiplication is a bit harder. They kind of show the formula here. So cool. Let's use this. So this is just going to be called complex. We're going to import complex, exposing complex. And something else is wrong. Oh, I haven't written any of these functions. So calculate max iterations. And this is going to be our C value in the formula. And for now, let's just return 1. And let's fill this in. Compute cell. Okay, let's just temporarily put model in there. Complex does not expose complex. Okay, well, let's expose that. Guess that's another good reason for copying this in. Okay, so that compiles. Now, compute cell, what we want to do is calculate the new value. And that's going to be done by calling calculate with max iterations. Let's just say 100 for now. And a complex number. So let's just pass 0, 0 for the moment. And then we want to update our model. So we're going to say computed equals dict.insert. Our new value. We need the location. Column and row into the old computed dictionary. This fixed point is saying that we're missing a viewport in our model, and yes, that is true. I'm going to be adding it to the model later on, but I usually like to start just by hard coding it. So we're actually going to hard code a viewport into this compute cell function, I think. All right, so here's my compile error. Compute cell is wrong. Oh yes. Value is a maybe int, so we actually want to say case value of, and if we get iterations back, we'll update it, and if we don't, we'll just return the old model. Actually, maybe we should technically remove. Then we'll say computed equals dict.remove colon row. Make sure that that value gets cleared out. No, dict.insert will not fail. It's just going to overwrite the current value, regardless of if there was a previous value or not. Okay. So we've computed this one cell, but we've done a fake calculation. And we've also done a fake coordinate. So let's write our real calculation now. So let's see if I can just do this from the description that I gave earlier. We're gonna, need to make this a recursive function. So we have max iterations, and we have our C, and we actually are going to need to iterate. So we're also going to want to pass the number of iterations that we've already done, which is an int, and another complex number, which is our current Z. I think we're going to need all that stuff. So let's try this out. So we're going to make our new Z, call it Z prime. And we said we're going to square, we're going to take Z prime equals Z squared plus C. So we can use complex.mult, I think it's called. Yeah. And we'll just multiply Z and Z. And then we're going to add c to it. So that should give us our new z value. And then we said if the size of z prime is greater than 2, then we're going to return just with the number of iterations that it took. And if it doesn't, if it's still within the range of 2, then we're going to iterate again. Calculate, and we'll have the same number of max iterations. We'll have the same c, but now we're on iterations plus 1, and our new z is z prime. So we're just going to recurse into this function. And let's see, we're also missing what happens if we exceed the number of iterations, so let's check that too. So if iterations is greater than or equal to max iterations, then we're going to return nothing and say that we never completed, or it never escaped. And then if it does escape, we're going to return how many iterations, and if it hasn't escaped yet, we're going to iterate, or we're going to recurse. I think that is the right calculation. So let's see if it compiles. Nope. Maybe .just is causing a problem. Oh yeah, line 51. Actually, the problem is here. We added parameters to calculate. So our initial iteration is going to be 0, and our initial z is actually going to be c. So let's define c. So technically, z starts at 0, but 0 squared is always 0, and then you add c, so we're just skipping the first iteration and starting with c. So that's like a tiny little optimization. Yeah, Arkham, and if you call dict.remove and there's nothing, it'll still be nothing. Cool. So now actually we have the hard part, because we need to determine the complex number that corresponds to the pixel we're at. So let's see. So maybe that won't be too hard. I want to start with a hard-coded viewport of 0, 0 in the corner and 2, 2 in the other corner, just because it's kind of an easy calculation, and we will set a custom viewport later on. So we're going to take our complex number, and the real part, the first parameter, is going to be based on the x position, or the column. So I want to just say column divided by model.width. We need to float both of these. And then multiply by 2. So this will give us a percentage of how far, and we'll multiply by 2. Okay, let's start with that. And we'll do the same thing for the row. We'll figure out how far into the pixels, Cool. Mikey's asking if we could start with max iterations and decrement it. We could, however, I wanted this to return the incrementing number of iterations it took. So I wanted to keep passing iterations in so that we, like, if we subtracted to get the actual number of iterations it took, we'd still have to pass the real max iterations through to subtract at the end. But if you wanted to not have, if you wanted to allow this to be decreasing based on as the iterations increased, I'm getting tripped up trying to talk about it. But yeah, you could potentially get rid of one of these parameters if you subtract it by subtracting, but then the return value would be basically flipped around, which may be fine depending on how you want to color this thing. All right. So let's see. I'm actually going to put debugging in here. And we're going to debug the toString of C and see what the calculation is. So let's check this out. So our complex number was 0.1 plus 0.1i, and that value never escaped. That actually seems reasonable, I think. Let's try calculating the cell at 99.99. And yeah, there we go. So this one is practically at 2, and it escapes in fact, the first iteration. And we've colored it yellow, if you can see that. So I am guessing and hoping that my compute cell, or excuse me, that the calculate function is actually correct. So now that we can compute one cell at a time, all we need to do is build up functions that can compute entire rows and then compute the entire grid. So before we do that, let's commit. So we basically added all of our computation, and we pulled in this complex number package. Calculate single pixels. There we go. Oh yeah, we could actually put max iterations in the model. That actually sounds good. Well, does it? Potentially, like a lot of Mandelbrot programs do dynamic iterations, whereas you zoom in, or it determines how many iterations it should do based on your zoom factor. So I don't think I want to pull it up into the model. But we could maybe make this a constant. Just stick that up here for now, so it's easy to change. All right. So let's compute rows now. So instead of using compute cell, I want to change this to compute row. We'll compute row 5, and let's compute row 6 also. So let's write that function. Compute cell, compute row. So let's do that down here. Compute row is going to take the row number and a model and give us back a new model. So we're basically going to use this range trick again. But in this case, we're going to fold, because basically we're going to start with our initial model, and then we want to go through each of the row numbers and merge those two things together via a function to get a new model. So we're going to have some function here. We're going to start with our model, and then the things we're going to map into that are going to be 0 up to model.widths. So actually for this row, we're going to loop through each column in it. Yeah, Danny's saying they might be dropping this range syntax in the next version of Elm 0.18, which potentially is true, but if that happens, there's just going to be a function called range, probably in the basics module or maybe in the list module. that you just use to do the same thing. Although actually this is not super optimal since it's generating this entire list. So if we were doing a huge array, we'd probably want to rewrite this to be a recursive function, which Elm will optimize if you do tail recursion. Okay, so what we want to do is call compute cell, and I'm actually going to mess with how the arguments are passed to make this curry nicely. So we want to pass the row into it, and then with fold, it's going to pass us another argument, which is the column number, and then another argument, which is the model. If we change our compute cell signature to take the row first, and then the column, and then the model, then this will all curry nicely. So row, column, model. All right, let's try this out. Yeah. Okay, so we computed a bunch of stuff, and we see some things changing. Let's add a couple more rows. Make sure. Let's see, 10, 20. Okay, a bunch of those are the same, but this one row down here is a different. So this may, in fact, be correct. And if not, we will find out shortly when we calculate the whole grid. Alright, so we have now calculated rows. Git commit -m. Calculate full rows. So I think we have two more steps. We want to compute the entire grid, and then we want to be able to have custom viewports. So we'll say compute all. And I guess a nice thing about the way we've built this up is that we now have these nice public functions to compute individual cells and rows. So if we wanted to write something that would like intermittently compute different parts of it over time so that it's not all computed up front, we could easily do that using these other functions we've exposed. So compute all is going to take a model and give back a model. And we're basically going to do the same trick. We're going to fold over each row number and call compute row for that row. So we're going to call compute row, starting with our model and looping through all the integers from 0 to height. And we don't need these parens. Let's see. Okay, it's chugging along. Hey, and there we have in fact computed something that looks reminiscent of a Mandelbrot set, or at least one quadrant of it. Yeah, okay, that was super slow. Let me take the debugging off of here. Let me kind of benchmark this. 2, 3, 4. Okay, it took about 4 seconds to calculate that. I'm gonna actually take this debugging line off, see if that speeds things up a little bit. There it is. Oh yeah, that was like instantaneous. Okay, so debugging is super slow in Chrome at least. Maybe it's faster in Firefox. Cool. So let me commit that, and then we will add a custom viewport. And then I guess maybe we'll take a quick break after doing the custom viewport and then add some colors after that. And then maybe I'll ask in chat where we want to go from there after that. I still have a bit of time today. calculate the entire grid. All right. So custom viewport. I guess I'm hesitating because this is the math part that's not that fun. All right. So here is how we're gonna do this. I think in the model, we want to say we want to have a min, which will be a complex number, which will be the top left corner, and a max, which will also be a complex number, which will be the bottom right corner. And let's see, our min will be complex, complex.complex, -2, -2. Since 2 is our escape radius, let's just do 2 on each side. And there's our max. And that still compiles. So here, when we calculate C, now we need to take the min and the max into account. So, to calculate the real part, we basically want to interpolate between the real part of the min and the real part of the max in the viewport. So let's see, the formula is basically going to be min plus max minus min times our percentage. And the percentage is determined by this. Okay, so I think we can get the real and imaginary parts out of the complex number just by destructuring the record. We look at this, complex is, yeah, just a type alias, so we can just refer to these internal fields directly. We don't have to call functions, which will make this look a little nicer. So, for the real part, we're going to take the min, which is model.min.the real part, plus model.max.real minus model.min.real times this stuff. And I'm actually gonna make call percent. Let's just define these up here. Call percent equals that. Row percent. This is saying, like, if the whole thing's 100 pixels and we're at pixel 50, this will be 50%, like halfway across. Then we'll do the same thing for the imaginary parts with the row percent. And let's see. Elm's picky about how these let statements are indented. Cool, I got the typo. Thanks, Arkham. Bam, does this work? Oh, yeah, it works. Cool. So we can set our viewport. Yeah, previously we were just going from the center of this down to the right corner. Let's see. So I want to tighten up the viewport a little bit. So in the real part, we only want to go to 1. That'll stretch it out. And then we want to make this 1.5, 1.5. There we go. And maybe we can up the iterations. And maybe we can make this a little larger. Make this 400. Oh, now it's slow. Hey, we got it though. Awesome. All right. So I want to take a quick break. When we come back, I want to add coloring based on the number of iterations that it takes to escape. So right now, all the yellow points are where the value of z eventually got larger than 2. So I do want to do coloring. And then, yeah, I'd like to take some suggestions from the chat. We could try to make this interactive, and like you can click somewhere to change the viewport and zoom in. Another thing we could try to do is to make this calculate incrementally, like to calculate one row and then fire off a command to like do it asynchronously and come back and do each row in a different update cycle. So that'll make it faster to compute, and also might be an interesting way to look at how to compose effects. So one of those two things potentially, or if there's any other ideas you want to try. Oh yeah, I said maybe we can extract the view functions for drawing graphs and like make a little package and publish that package. So we can do maybe a couple of those things, depending on how fast things go. So let me push this. Whoa. Oh shoot, you can't use exclamation marks in Bash, I forget. Arkham. Oh yeah, effects did go away, but they're called commands now. And there are still tasks. Cool. So, let's take a short break, and I will be back shortly. And yeah, let me know in the chat what y'all want to see.